Assalamualaikum warahmatullahi ta'ala wabarakatuh. Alhamdulillahirrabbilalamin. Wassalatu wassalamu ala ashrafil anbiya wa mursalin wa ala alihi wa sahbihi ajma'in. Alhamdulillah. So today what we're going to do in this short video, which I hope to help you in understanding the roles of dislocation in metals. Okay. So what are we going to do? We're going to look at this video and we're going to have some background on dislocation. We'll do some quick review what dislocations are all about. We talk about their motion, then we will link the motion of dislocation to permanent deformation, and then we'll talk about the significance of all this philosophy of dislocation motion causing the permanent deformation. We'll talk about the cause and effect kind of thing. Right. So first of all, let's remind ourselves about dislocation. What are they? Okay, dislocations are basically line defects. Okay, they are large-scale defects that result from changes to the lattice itself, and it's being demonstrated in this slide. As you can see, the atoms are not perfectly arranged at the border lines here, indicated by the red lines. So there are misfit at that border, and that is what's causing the dislocation. So dislocation is basically dislocated atoms. Okay, line of dislocated atoms. So that's what we call dislocations. How many types of dislocations are there? So basically what we learned, there are two types of dislocations. One is what we call edge dislocation. It's shown on the left side here, right, where you have the movement. If you can see here, the extra half plane indicated by the red line in the video here, that extra half plane is what we call edge dislocation, and it seems that it's moving from right to left in that picture, in that schematic, right? And if you look at the right side schematic, what actually happened when you have an edge dislocation, it's right here, right? This is where your edge dislocation, and can you imagine that extra half line of dislocation is actually compressing the atom surrounding it. So that's why we call the top area where the line dislocation is, where the edge dislocation is called the compression area, because that extra half plane is compressing the atoms on the sides, while the atoms at the bottom are experiencing tension because they are being pulled apart due to the compression on top. So whenever you have edge dislocation, you're going to have these two regions of stress and strain. Okay, so on the top you have compression, and on the bottom you have tension. So you can imagine that the lattice is experiencing some strain. So this is what we call lattice strain. Okay. How about the other type of dislocation? It's called screw dislocation. And what it is basically, if you look at this block, okay, it's basically a block of material being cut halfway. Okay, let's cut it halfway up to that point, and then what you do is you give it a shear. You push the top part to the back and the bottom part to the front. So you shear it, and what happened is that you're going to create screw dislocation. All the atoms along this line here, shown over here, will be connecting all the atoms that are being displaced because of your action shearing the block, right? So if you cannot imagine that, if you look on the right side, this is the 2D view of that block showing all the dislocated atoms. If you can follow my marker here, this small red dot here, this is the line connecting all the dislocated atoms from front to the back, and the line of dislocation is this line, okay, from A to B, because that is the line that connects all the dislocated atoms, and they look like a spiral, they look like a screw. That's why we call it a screw dislocation. Okay, so that are the two types of dislocations. Right. So what's so important about dislocation? What do they do inside the material? What are their roles? Actually, dislocations can do many things. They can multiply, they can nullify each other. But the most important thing I want to mention here is that dislocation provides a mechanism for atoms to move inside the material. There's so many atoms inside the materials, they do not know how to move. We have to provide them with a mechanism, with a way, with a method to move inside the material. So this is what happened in a material. If you have a dislocation, as shown over here in the left side schematic, you have an edge dislocation, and look at how it moves from side to side. Okay, so basically, instead of moving all the atoms at the same time, you only have to move one line of dislocation, one atomic spacing at a time. So at the end, all the dislocation will move, and it will give the change to the shape of the material. Okay, so let's see in the right schematic, or that video on the right, you see when you push the block from front and back, okay, you are changing the shape of the block. And what actually happened in the block is that you are pushing the dislocations, you are pushing the atoms to move along where? Along the dislocation. Okay, not all atoms will simply move, they'll move via or through the dislocation motion. Okay, so dislocation motion helps to move the atoms from one location to another. Right, when dislocation moves, they actually move in certain direction and on certain plane. So there will be always two components to dislocation motion. You have what we call slip direction and what we call slip plane, because slip is what dislocation motion is all about. When you have dislocation motion, we say it has slipped. So dislocation moves, it moves in certain direction and on certain plane, and the combination of this direction and plane we call slip system. All right, so this is shown over here basically in the schematic, where you have this block having an edge dislocation, and then with the application of shear force, right, you're going to force this edge dislocation to move from the center point to the right side of the block. And what happened with that movement, you actually have changed the shape of the block. When you change the shape of the block permanently, we call it permanent deformation, or what we call plastically deformed. So in this block, it has been deformed plastically or permanently, and it happens through the application of force, and that force has made the dislocation to move. Okay, so that is what we mean by having dislocation and causing the plastic deformation. Right, so we were talking about permanent deformation. So in the video on the left side here, what you can see, you see this is one type of processing, what we call rolling. If you can see, there are two rollers on the top and the bottom here. This is the top roller and the bottom roller. And what do? You feed between the two rollers with this sheet, this metal sheet. Initially it's just a flat sheet, right? And then because of the force applied between the two rollers, when it come out from the rollers, now it is bent. It gives a different shape from flat into a V-shaped sheet, right? So you have caused permanent deformation to the metal sheet. And if we look at what happened inside the atoms, okay, if you look inside the material and what happens to the movement of atoms inside and how the dislocation has played its role, okay, how this is the block of material having all the atoms inside, and you see on the right side you are applying the load. As you apply the load, your edge dislocation will move from one side to another, and finally what happened is that you have changed the shape of the grain, okay, from the initial squarish shape into a distorted square shape. All right, so that means you have dislocation motion happening. You force it to happen by the application of force. You eventually cause the change in shape because of the movement of the dislocation, and finally we said we have achieved plastic deformation, meaning permanent deformation. Alright, so what is the cause and effect relationship that you have seen in this short video? We have seen that dislocations in metal play a vital role in plastic deformation. A very important role in plastic deformation. By how? But the dislocation must move. It has to move in order to facilitate. Okay, dislocation motion has to move to facilitate plastic deformation by giving the mechanism for atoms to move once a force is applied onto them, right? Now, if dislocation motions are favored, if you are making dislocation motions to happen easily, that means plastic deformation becomes easier. Okay, don't have anything to block the motion. That means with a little force that you give to the material, it will easily be deformed. On the other hand, if the dislocation motions are being impeded or being hindered or is being blocked by whatever ways that you can think of, the material becomes harder to deform, and thus we call it the material becomes strengthened, right? So in one case you may want to deform the material easily, for instance in processing the material, in producing a product, okay, and on the other hand you also want, sometimes you want to strengthen the material. So how do you strengthen a material? You have to think about how to stop or block the dislocation motions. So all in all, what we are trying to tell you in this video is that we want to make you see how a dislocation in a material play its role by its motion, which it will cause deformation to the material. And you can also reverse the effect. If you want to strengthen any material, then you can think about stopping or blocking the motion. So dislocation motion is the key word. If you make it easy to happen, it's easy to deform. If you make it difficult to happen, you're going to strengthen the material. So that is your job as an engineer, whether you want to make it easy to deform or you want it to be strengthened. Thank you. Thank you for listening.